For this video, I'd like to further discuss these even and odd functions. And I've redrawn these graphs for essentially the most basic even and odd functions. Remember, this one here is an even function. This one here is an odd function. And you may have noticed that the exponent is even here and the exponent is odd there. And that's not a coincidence. In fact, that's likely how these names came about. But you would also see y is equal to x to the fourth, y is equal to x to the 10th, or basically y is equal to x to any even power. That would be an even function, or it would have symmetry about this y-axis. So all of these functions, no matter what even power I raise it to, they would all be symmetric about this line, or this y-axis here. And for these odd functions, kind of a similar thing is true. Functions like y is equal to x to the fifth, y is equal to x to the ninth, or y is equal to x to any odd power. These all look very similar to this graph here, and they all exhibit odd symmetry. Namely, they are symmetric about this origin here. So you can imagine if we did a 180 degree rotation about this origin, then you would end up with the exact same picture. And that's true for each of these. So any function where you have x to an odd power, and that's the only term. Now, if you start adding in other terms, it gets a little bit more complicated, and that's something we'll talk about at the end of this video. But what I want to mainly focus on in this video is essentially the algebraic properties that come out of these symmetries. So let's first start with these even functions. And basically the symmetry that we talked about in the introduction video is that if we pick a particular x value, let's say x is 2, and that gives a y value of 4, then when we choose the opposite x value, we would get the exact same y value, namely that value of 4. So essentially what this means is that when we put the opposite x value into the function, we get the exact same function value. So you get back f of x. And you can see this if I take y is equal to x squared and I put in minus x anywhere I see an x, I should get back the exact same function. So let me actually write this using function notation so it's a little bit more clear. So with this y equals x squared, we'll rewrite it as f of x equals x squared. And that's just because y and f of x are the same thing. And what we're going to do is plug in minus x and see what we get. And if it's an even function, we'll just get back the exact same function that we started with. So if it's even, we should get back x squared. So if I plug in negative x anywhere I see an x, and I'm squaring that, and a negative times a negative is always a positive. So you do get back the original function. So this right here is essentially the key algebraic feature of even functions. And we're going to use this property to essentially determine whether or not any given equation is even or odd. So let me clear a little space and then we can talk about these odd functions. And now that we have a little bit more room, let's focus on the key feature of these odd functions. So essentially we're asking, what is the algebraic feature to determine the symmetry of these odd functions? So recall that with an odd function, if we choose a particular x value, let's say x equals 1, and that gives us a y value of positive 1, then when we choose the opposite x value, negative 1, we should get the opposite y value. And if we want to write that down formally, like we did for even functions, essentially if we take our function, we plug in the opposite of x, we should get back the opposite y value. So f of minus x would equal minus f of x, and this is the key algebraic property to determine the symmetry of these odd functions. And we can test it just so that you can see that it works based off the example we have. So we're going to plug it into this y equals x squared, or x cubed. So I'm going to rewrite that first using function notation. So we have f of x is x cubed. That's this function here. And just remember that y and f of x are interchangeable. And then what I'm going to do is plug in minus x anywhere I see an x and see what happens. So I get minus x cubed, and then if I simplify this, a minus times a minus is a positive, but then I have to multiply by another negative, So this ends up becoming minus x cubed. And you can see that since x cubed was our function, then what we ended up with was the opposite. This is the opposite of our starting function. And like I said, that is the key feature to determine these odd symmetries. So essentially this result here and this result here are the two key ideas we're going to use going forward when solving these problems.